3.2 measures of variation. According to this book, variation is the single most important topic in statistics. So this is the single most important section in this book. This section presents 3 important measures of variation: range, standard deviation, and variance. I think range is the easiest. Standard deviation and variance are a lot harder. These statistics are numbers, but our focus is not just computing those numbers, but developing the ability to interpret and understand them. Here we've got this round off rule, and we've seen this before. It's saying carry 1 more decimal place than is present in the original data. So we've seen that round off rule before. The range of a set of data values is the difference between the max and the min. This is about as easy as you can possibly get. Range is max minus min. Important properties of range. The range uses only the maximum and minimum data values, so it is very sensitive to extreme values. The range is not resistant. So you've seen this definition before of resistant in the last lesson, and it's talking about how much the outliers affect the numbers. All right, range is not resistant. That means that any outliers are going to greatly affect the value. Because the range uses only the maximum and minimum values, it does not take every value into account, and therefore does not truly reflect the variation among all of the data values. Number 1, find range. So this is quite simple. All we have to do is take the max minus the min. $55.6 minus 14.1 is 41.50. So there's that round off rule where we keep 1 extra decimal point. 41.50 is the range. The standard deviation of a set of sample values, denoted by S, is a measure of how much data values deviate away from the mean. And I think that's kind of a tough concept, but let me give you an example here. All right, an example. Here's a list of 4 numbers. If I had you find the mean of those 4 numbers, you ought to be able to do that in your head. Add them up, divide by 4. The mean of those numbers is 10. Remember that symbol, X bar, was the mean, okay? When we're talking about standard deviation, we're talking about how much do those numbers differ from the mean. So this is a simple example where the standard deviation is 0 because those numbers don't differ at all from the mean. They're exactly the same as the mean. Now, let me give you another example. If I said 0, 5, 15, 20. If you calculate the mean of those numbers, add them up, that's 60, divide by, add them up, that's 40, and divide by 4, that's 10. This average is also, this mean is also 10. I can't do the standard deviation in my head there. I don't know. We haven't really seen how to compute standard deviation yet, but I know it's not 0. Standard deviation is talking about how much those numbers differ from the mean. And that second example there, you can see those numbers are all different from the mean of 10, whereas in the first one, they didn't differ at all. So that's kind of what we're talking about. How much do those numbers differ from the mean? We've got a lot of new symbols and weird symbols and different symbols today, so focus on those. S stands for sample standard deviation, and this is the Greek letter sigma. It's actually lowercase. We've also got an uppercase sigma that means something else, but this is lowercase sigma, and it's population standard deviation. All right, so they give you a couple of equations, and I'm not going to expect you to memorize these equations, but you are going to have to be able to use them. Sample standard deviation is here, and I know that looks really complicated, but you've seen these symbols before. You've got that big square root, and you've got this capital sigma right here. And if you recall, that means sum. That means we're going to add some things up. When you see this X, it's just talking about all of the data values that we have. X bar, of course, is the mean. and we're going to have to subtract them. We're going to have to square it, and lowercase n is the number of numbers. So we've got these symbols, and if you don't remember what the symbols mean, then it's going to be really hard for you to actually calculate and do that formula. Ironically, they give us another formula and they call it a shortcut, but it looks like it's going to be harder. So there's a second equation for calculating standard deviation of a sample. It looks like it's going to be harder, but it's actually going to be a little bit faster. All right, so we've got those two equations so far. We'll have more. Important properties of standard deviation. Standard deviation is a measure of how much data values deviate away from the mean. The value of the standard deviation, S, is never negative. It is 0 only when all of the data values are exactly the same. So, that's like what I was talking about earlier. If I give you all the same numbers, then yeah, of course that standard deviation is 0. Larger values of S indicate greater amounts of variation. Standard deviation S can increase dramatically with one or more outliers. The units of standard deviation S, such as minutes, feet, and pounds, are the same as the units of the original data values. The sample standard deviation S is a biased estimator of the population standard deviation. Okay, so notice they're talking about sample standard deviation, and then there's also population standard deviation. So you're going to have to think about the difference between a sample and a population from an earlier chapter. Population, of course, is all of the numbers, and sample is just some of the numbers, right? So we've got like a couple of formulas, but we've also got to think about whether it's a sample and a population. A lot going on in this lesson. So this means that the values of the sample standard deviation S do not center around the value of sigma. We'll come back to this term biased estimator later. Example 2, calculating standard deviation. All right, now you want to write really small here because there is a lot going on in this. I'll show you later how to do it with technology, but for right now we're gonna do it by hand. Okay. Now, I probably should have included this chart. I probably should have included this chart in the notes. This is the steps for how to do standard deviation. So you can take a picture if you want, or if you go to the book, find page 100. This is on page 100 of the book. Regardless, I don't know that you really need these steps, because all it's doing is just walking you through the formula. So let's do this. The formula for standard deviation was S equals big square root of sigma x minus x bar squared all over n minus 1. All right, so write that down somewhere, top of the page. That's that equation for calculating standard deviation. And the steps are essentially just do order of operations on this equation. Okay, so imagine if I was looking at this equation and how I would actually have to calculate this formula. The first thing that you would want to do is go inside the square root, go inside the parentheses, and find x bar, which is the mean. All right, so step 1, remember, write small. We're going to find x bar, which is the mean. Remember how to find the mean. You add up the numbers and divide by the number of numbers. So 38.5 plus 55.6 plus 22.4 plus 14.1 plus 23.1 divided by the number of numbers, which is 5. We actually already did this problem in a previous lesson. We added those numbers up. You might recall we got 153.7 over 5, which is 30.74. That is not the answer. That is not the standard deviation. That is the mean. Okay? So just think about it. Look at the equation and think about order of operations. If I'm thinking about order of operations, the next thing I'd have to do is still inside the parentheses, I would take x minus that x bar. And I remember what x is. X stands for each one of those data values. X means each one of those numbers. So when I do step 2 and I'm doing x minus x bar, what I have to do is take 38.5 minus the mean of 30.74 and 55.6 minus the mean, 22.4 minus the mean, 14.1 minus, and 23.1 minus. Each of the x numbers minus the mean. And so when I subtract those, 38.5 minus 30.74, I get 7.76. In the next one, I get 24.86. And the next one, negative 8.34. Negative 16. Oops. .64, negative 7.64. Okay. So if you're looking at the equation, if you're thinking about order of operations, you might be able to guess what's next. We have to take that difference and square it. So step 3, I'm going to take each of those differences and square them. What I mean by that is 7.76 squared, 24.86 squared, negative 8.34 squared. Make sure you put it in parentheses, otherwise your calculator won't square the negative. You have to square the negative. Negative 16.64 squared, negative 7.64 squared. So once I square those numbers, 60.2176, 618.0196, 69.5556, 276.8896, 58.3696. Okay. Squared all of those numbers. Notice the negatives go away. Of course, that's going to happen when you square a negative. All right. Anybody know what's next? We've got to do the sigma next. Not going to divide yet. We've got to do the sigma next. Sigma, of course, means sum. So we're going to add those numbers together. So I'm going to put this in a different color. I'm going to put it right here. Okay. Step 4, we've got to do the sigma of the difference squared. So all I'm doing is adding those 5 numbers. I'm going to add those 5 numbers together. 60 point plus 618 point plus 69 point, blah, blah, blah. Okay. I add those numbers. I get 1083.0520 equals. Okay. So all I'm doing is just going through the equation. Next thing, I'd have to divide by this n minus 1. So I'll go ahead and come over here. Step 5, I've got the sigma of the difference squared. I'm going to divide by n minus 1. Now, n is the number of numbers. N is 5, remember, right? So all we have to do here is divide that 1083.0520 by n minus 1. 5 minus 1 is 4. So we're dividing by 4. And we get 270.763 0. One more thing. Square root. Very good. I still have to do the square root. So the last step, I'm going to do the square root of the sigma of the difference squared over n minus 1. So it's just the square root of 270.7630. And I get 16.45 megabits per second. That is the standard deviation. Now again, we're not always going to have to do that by hand. There is technology that will do this for you a lot faster. All right, but there it is. And that's how I did it. And it wasn't rocket science. All I did was walk through that equation. What does that mean? Standard deviation. Remember, we're talking about how much do these numbers vary from the mean. That's what we're talking about. Or deviate from the mean. Example 3 is really the same thing. It just says we're going to use the shortcut formula. All right. So the shortcut formula, let's write that down real quick. N times, square root of n times sigma x squared minus sigma x squared. Notice that's different. Over n times n minus 1. So I know this one looks more complicated, but it's actually a little bit quicker. We don't have to start here, but let's just start here by doing sigma x, okay? So step 1, if I do sigma x, all that means is the sum of the x numbers. So it's just saying add the numbers together. 38.5 plus 55.6 plus 22.4 plus 14.1 plus 23.1. We've already done that. The sum of those numbers is 153.7. Okay? So this is a little different than the last one. Step 2, I'm going to go inside here. And I'm going to do the sum of x squared. And so I messed this up earlier, but I'm not going to mess it up this time. The sum of x squared just means we're going to take those same numbers, square them, and add them up. So I want 38.5 squared plus 55.6 squared plus 22.4 squared plus 14.1 squared plus 23.1 squared. So it looks very similar. We're adding the numbers, but we're adding the squares of the numbers. You add all that up, and that is 5807.79. Now, I don't know if you'd really call this a step, but n is 5, right? We know n is 5, so that's going to go here and here and here, where n is 5. I would plug 5 in 3 different places in that. And that's really all I need to do for setup. I can go straight to the next step, the last step, just plugging stuff in. Okay? Big square root, and I know n is 5, so I plug that in. And then that first set of parentheses was sigma x squared. That was 5807.79. Ran out of room here. Let's try that again. Minus, the next thing I have there is sigma x. That is 153.7, but then I'm going to square it according to that equation. On the bottom, I'm going to have n is 5 times parentheses 5 minus 1. Look like that. So all I'm doing is plug and chug at this point. In the top of the fraction, I have 5 times 5807.79 minus 153.7. If you clean that up, that's going to be square root of 54 15.26. And on the bottom, you'll have 5 times 4 is 20. So we do the division. We're not going to do the square root yet. That'll be last. But you divide 54, 15, 26, and 20, and you get 270.763. And that number might look familiar to you because we saw that number pop out last on the last example. We take the square root of that, and we get 16.45 megabits per second. Same answer. So that way is a little bit quicker. It's a little bit less work. I know it looks like it's going to be more work, but it's a little bit less work to find the same standard deviation. That's why it's the shortcut formula. Changing gears, we've got the range rule of thumb for understanding standard deviation. The range rule of thumb is a crude but simple tool for understanding and interpreting standard deviation. The vast majority, such as 95% of sample values, lie within 2 standard deviations of the mean, okay? And I remember as a student having a hard time with that concept. But when you see all these symbols, remember this symbol was talking about the mean. I know that's not the one we saw today, but we saw it in the last lesson. That was the population mean, but that was the mean. And so what they're trying to do is they're trying to add 1 standard deviation, 2 standard deviations. Okay, so what this says is the mean plus 2 standard deviations. And so what they're saying is anything to the right of that on a number line or anything more than that is called significantly high. And then if you go back 1, 2 standard deviations, anything less than that number right there is called significantly low. Values in between those 2 numbers, in between 2 standard deviations from the mean, would be called not significant. Range rule of thumb for estimating a value of standard deviation. This formula right here is a rough estimate. Okay, so for example, with example 2 and 3, actually, we just calculated the standard deviation was, what was it, 16.45? That was the standard deviation. But this range rule of thumb for estimating the value says we can do the range divided by 4 and get kind of close. All right. So remember when we did the range, that was our first example. The range for those numbers was 55.6 minus 14.1, which was 41.5. So this formula says just divide that by 4. And if you divide that by 4, you get 10.38. Okay. Now that is not the standard deviation. This is just a rough estimate. So the answer, remember, was 16.45, but this is just kind of getting us close. Ballpark, 10.38. That's a pretty rough estimate. Now we talk about standard deviation of a population. A different formula is used. Okay, instead of dividing by n minus 1, we divide by the capital N. So remember what capital N was. Capital N was the number in the population. Little n was the number in the sample, but capital N was the number in the population. So it looks like a completely different formula, but we've got a lot of the same elements here. We've got this square root, and we've got this sigma, and we've got this difference, and mu was the mean, right? And so it's really very similar, except we're dividing by this big N instead of n minus 1, little n minus 1. Variance of a set of values is a measure of the variation equal to the square of the standard deviation. So they're saying variance equals standard deviation squared. That's what they're saying, okay? But I always remembered it a different way. I always remembered it as standard deviation is equal to the square root of the variance. those two things say the same thing. Sometimes one of them is more useful than the other, and vice versa. All right. So I prefer remembering it this way, but it really says the same thing. Standard deviation is the square root of the variance, or variance is the standard deviation squared. I think the key for you is to try to nail down these symbols. Little s is talking about sample standard deviation. So s squared is the sample variance. This lowercase sigma is the population standard deviation, and they're not the same. Okay, there are different numbers. So sigma squared would be population variance. Important properties of variance. The units of variance are the squares of the units of the original data value. And that should make sense because variance is equal to the standard deviation squared. And so, of course, the units are squared. We're talking about inches squared instead of just inches. The value of the variance can increase dramatically with the inclusion of outliers. This variance is not resistant. So here's that word again. We've seen that several times in the last two lessons. Resistant is talking about how much outliers affect it. Okay. Not resistant means that outliers really greatly affect that number. The value of the variance is never negative. It is zero only when all the data values are the same number. The sample variance S squared is an unbiased estimator of the population variance sigma squared. So we'll talk about this term here in a second. Why divide by n minus 1? There are only n minus 1 values that can be assigned without constraint. With a given mean, we can use any numbers for the first n minus 1 values, but the last value will then automatically be determined. Okay, so I think that's kind of difficult. You might want to read that again. I think what that's saying is if we know the mean and we know all but one of the numbers, then that last number is set. Okay, the last number is automatically set, and so we don't need it. With division by n minus 1, sample variances tend to center around the value of the population variance. With division by n, sample variances tend to underestimate the value of the population variance. Again, I think both of these paragraphs are pretty hard to read. Anytime you come across something that you don't understand the first time, you better read through it 2, 3, 4 times. All right, read through that a couple of times, try to understand that. Empirical rule for data with bell-shaped distribution. The empirical rule says that for data sets having a distribution that is approximately bell-shaped, the following properties apply. Okay, now wait a minute. Empirical rule is going to be really useful, but you need to understand that it only applies with bell shapes. Okay, if it's not bell-shaped, you got to use something else. So this empirical rule will be useful if it's bell-shaped data. Okay, so they're saying about 68% of all values fall within one standard deviation of the mean, about 95% fall within 2 standard deviations, and about 99.7 fall within 3 standard deviations. So I think it's easiest to understand if you look at this picture. Okay, think about a number line. And you've got a bell-shaped distribution of data. The mean is right here in the middle. That's the mean, okay? And then what they're talking about is take that mean and you add 1 standard deviation or you subtract 1 standard deviation to get some kind of range of numbers. Essentially what they're saying, I'm going to round off here, but the 34% of the numbers are right here and 34% of the numbers are right here. And so what they're saying is 68% of the numbers are 1 standard deviation from the mean, or within 1 standard deviation from the mean. If you go out another standard deviation, I like to call this 13.5 and 13.5. If you add up all the values there, then you'd have 95% of the numbers are within 2 standard deviations from the mean. Let's talk about how many numbers there are in that data set. And then if you go out another or third standard deviation in either direction, they're saying 99.7% of the data or of the numbers are within 3 standard deviations of the mean. There are still a few numbers out here in the extremes, but more than 3 standard deviations away, but not very many. Okay, so that's the empirical rule. And I think you'll like doing empirical rule questions, all right? IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. What percentage of IQ scores are between 70 and 130? I think that question looks tough at first, but it says it's bell-shaped distribution, so we can draw this picture. I would start with a number line, and since it says there's a mean of 100, I'm going to put that in the middle. Okay, so I've got my bell-shaped distribution. 100 is right in the middle. Okay. So when they say there's a standard deviation of 15, then what that means is if I add 15 or I subtract 15, then I would know that about 34% of the numbers are here and 34% of the numbers are here. Okay, that's what I would know. That doesn't answer the question yet because they're talking about between 70 and 130. So you need to go another standard deviation. 15 is the standard deviation. So let's add another 15. If I add another 15, I'm at 130 right here. And if I subtract another 15, I'm at 70 right there. And those are the numbers I need, right? So if you look back at those percentages on the empirical rule, 13.5, about 13.5. So about 13.5% of the numbers are here, and about 13.5% of the numbers are right there. So the question, what percentage of IQ scores are between 70 and 130? Well, you just add up those 4 numbers, right? 13.5 plus 13.5 plus 34 plus 34 is what? 95? That's 95%. 95% of IQ scores are between 70 and 130. Okay, the answer is 95%. If you wanted to go more, I think it's interesting to go another one. Add 15 more, add or subtract 15 more. We could say that, what was it, 99.7? 99.7% are between 55 and 145. 99.7% of all IQ scores are going to be in between those scores, 55 and 145, right? That wasn't the answer, though. The answer to this question was 95. I remember not learning what Chebyshev's theorem was, okay? Chebyshev's does kind of the same thing, all right? But the difference is Chebyshev's works for any set of data. Empirical rule, it had to be bell-shaped. So doesn't have to be bell-shaped. This is more versatile, I guess. Chebyshev's works every time. Empirical rule only works if it's bell-shaped, okay? So the proportion of any set of data lying within k standard deviations of the mean is always at least 1 minus 1 over k squared, where k is any positive number greater than 1. That's Chebyshev's theorem, okay? And I think that's hard to read and hard to understand, but look at an example, all right? If k equals 2, so for k equals 2, Chebyshev's would say 1 minus 1 over 2 squared, which is 1 minus 1/4 or 3/4, okay? And so what Chebyshev says is at least 3/4 of the values lie within 2 standard deviations. Okay, so it's kind of saying the same thing as that bell shape. All right, it's not a bell shape, but that's what we were talking about. We were talking about within 2 standard deviations. Come on, where'd he go? All right, but the difference is we don't have to be talking about bell shape. We can talk about anything. So for k equals 3, Chebyshev says 1 minus 1 over 3 squared, 1 minus 1/9 is 8/9. So it says at least 8/9 of all values lie within 3 standard deviations. That's all it says. That's all Chebyshev says. And it's trying to do the same thing as the empirical rule. So number 5, IQ scores have a mean of 100 and a standard deviation of 15. What can we conclude from Chebyshev's theorem? So don't draw the bell shape because we don't know if we have the bell shape right here. We've got the mean right in the middle and 1 standard deviation away. So add 15 or subtract 15. Okay. 2 standard deviations away would be 130 and 70 right here. Okay. We can even do 3 standard deviations, go to 145 if we add 15, and subtract 15, that's 55. Okay, Chebyshev's says for k equals 2, 1 minus 1 over 2 squared, 1 minus 1/4, or 3/4. Okay, Chebyshev's says that at least 3/4 of IQ scores are between 70 and 130. Okay. For k equals 3, k equals 3 is talking about 3 standard deviations away from the mean. 1 minus 1 over 3 squared is 1 minus 1/9, or 8/9. Chebyshev says at least 8/9 of the IQ scores are between 55 and 145. That's Chebyshev's. All right, getting close. Comparing variation in different samples or populations. The coefficient of variation, CV, for a set of non-negative sample of population or population data, sample or population data, expressed as a percent, describes the standard deviation relative to the mean and is given by the following. Okay, I know it's another formula and another thing that looks confusing, but what we're talking about here is standard deviation divided by the mean times 100. Okay, and this is the same thing. It's the same thing over here. It's standard deviation divided by mean times 100. Same thing, same thing. Okay, what we're trying to do is we're trying to compare variations. All right, this is good to compare variation when the means are very different and also when the units are different. So if we were trying to compare lists of numbers and one's talking about lengths in feet and the other one's talking about weight in pounds, all right, it'd be hard to compare those numbers, but this makes that comparison possible. Round off rule for the coefficient of variation. This one says round to 1 decimal place, which is different than the round off rule we had before that said keep an extra number. I think it's weird when they change it up, but they did here. Last slide, biased and unbiased estimators. I'm going to need to read this slow, probably read it a second time. The sample standard deviation S is a biased estimator of the population standard deviation S, which means, wait, isn't that sigma? Which means that the values of the sample standard deviation S do not tend to center around the value of the population standard deviation, okay? I think you might need to read that again. Biased estimator, all right? Then the sample variance S squared is an unbiased estimator of the population variance sigma squared, which means that values of S squared tend to center around the value of sigma squared instead of systematically tending to overestimate or underestimate sigma squared. Very difficult wording. Definitely want to read that again. Look at that again for biased and unbiased estimators.